right, so go ahead and get that glued in if you have not yet already. If you want to label Chapter 2A Logic, that's what this whole chapter is about. And then the title of 2.1 is already there, so you don't have to write that. Okay, so get that glued in. Remember, there's only 2 glue sticks at each table, so you might have to share them. I can grab it. Alright, so reasoning means that there's like something behind it. There's reasons behind. If you give a reason, that means you're giving an idea. Okay? Yeah. She was like, I have to go.
Grace would like you to stop by at lunch.
For what?
So you can ask Mr. Alka.
Oh, because I need a picture. Can I just email it to I'm taking a nice picture tonight. Okay, a conjecture. A conjecture is a conclusion. Or it might be like a rule. Okay? A conjecture is like a conclusion or a rule. So if you make a conjecture, my favorite game to play, and no one ever plays with me because I'm so good at it, is Clue. And when you play Clue, you make conjectures, you make conclusions, and you say, I suspect it was Mrs. Peacock in the dining room with the candlestick. And that's a conjecture. You're making a conclusion. Okay? It's a great game. Alright, inductive reasoning. We're going to learn 2 types of reasoning this chapter. We're not going to learn the second type of reasoning until later on. But this first one is inductive. So inductive reasoning uses patterns to make our conjectures, to make our rules. We're just going to use patterns, or based on what we have, or what we are given. Alright, so we have 3 examples we're going to do in this first half of these notes. It's not really half, the first part of the notes. You guys have something so important that you have to write about it on a whiteboard? Yeah. It's that important. Alright, for these first 3 problems, we're going to create a conjecture. So we're going to come up with a conclusion on what's the rule. And then we're also going to come up with whatever the next term is. So in this first one, it goes 4, 10, 18, 28, 40. We need to figure out a conclusion, a rule. What's happening in this pattern? Multiplication? It's small to big. There you go. That makes more sense. I was like, what? It's small to big. So the numbers are getting bigger. They're increasing.
How are they increasing? How are they growing?
How could we go from number to number?
What are we going to add? 4.
4 plus what? 6 is 10. Do we just add 6 to 10 and it's at plus 6 plus 6 plus 6?
Plus 8 now.
Now it's plus 8.
20. That's what I said that. So.
You said 12. I heard it.
Yeah, thank you.
All right. And then what would be the next thing that we would add on to get the next number? 14. How did you get 14? How did you know the next thing we would add is 14? Yeah, it's like we're adding 2 to each of these numbers. So we're adding on, but every time we add on, we add 2 more. So it goes 6, 8, 10, 12, 14, then we'd add 16, then we'd add 18. Counting by 2s is tough some days. All right, so our conjecture is that we're adding on, but how many more do we add each time? add 2 more than before. So if before we added 8, now we're going to add 10. Is there 5? You need to have at least 5. Alright. Erica, yeah. I got it already. Alright. Then our next term, we're going to take that 40, and what are we going to add to the 40? 14. So we're thinking 40 plus 14 is what? 54. And this one just says just the next term, so we don't need to keep going. We don't need to do the 3rd, 4th, 5th, 6th. We're just going to stop at 54 there. Alright, next up. That one was a math problem. Now we got a word problem. That's a math problem. This is math. Khalid's doctor's appointments are December, May, October, March, ... So we have to try and figure out what is that pattern. For me, when I think months, I have to write out the months of the year. So I'm going to write down all the months. January, February.
It's fine.
You don't need the support of writing it out.
How much? One person in here.
August, September, October, November, December. Adding 5 what? So if I start in December, and then I have to go 1, 2, 3, 4, 5, that would give me May. Okay, then from May, how many months is it till October? 1, 2, 3, 4, 5. And then from October, it'd be 1, 2, but then we'd be back at January, 3, 4, 5. So maybe March. So it's every 5 months. So appointments are every 5 months.
So if we know that Khalid goes to the doctor every 5 months, when should he make his next appointment for?
And we left off in March. So if you left off in March, we're going to go 1, 2, 3, 4, 5, and we get August. You're right. I don't know my months very well by heart, so when I'm trying to count out, I'm trying to count too much, so I had to write it out. But you don't have to write it out if you can do it in your head. Nice job. Alright, next up we got this pattern. This one's a visual pattern. Okay, there should be commas in between here, so this is like the first one, second, third, this is the fourth.
So for this, we're going to try to draw in that next term. And there's a few different ways you might think about this, so have a look at that pattern and try to see if you can decide what would come next.
If you want to start drawing it out, you can. What's going to go next? Yeah.
You think you've got it, try drawing it out.
All right. What do you guys see? How do you know what the next thing is going to be? Plus 5? So there's going to be 5 more dots. How do you know where those 5 dots are going to go? Yeah, it's like climbing a staircase. Okay, so some people, they view this as like, here's the first dot, that dot went there, and we just put 2 below it. Now, these ones just traveled up, and we put 3 below it. Then we put 4 below it, so then we're going to do the same thing and put 5 below it. What's another way? Did anyone else think about it as something else rather than thinking it as stacks?
So you started with 1, then you added 2.
Like this?
Yeah, and then you're going to add 3. No.
What?
No, so she's saying move like left to right. So you start with 1, then to the right.
Oh, so columns.
Yep.
All right, so we did 1, and then 2, and then 3. Got it. And then 4, and then 5. Is that what you're saying, Olivia? Okay. Cool. So if we think about them as separate and we're just adding a column to the right, so add a column to the right with an extra dot. That might be your conjecture depending on how you think about it. What about if we just look from here to here? This 1, it was 1 dot on the bottom. Now it's on the bottom, sorry. On the bottom there's 2, and then it goes 3, add 1, 4, add 1, 5. In this row, we started with 1 here. It was 0. 0 plus 1 is 1. 1 plus 1, 2. 2 plus 1, 3. 3 plus 1, 4. So there's lots of ways you could either think of it vertically, you can think of it horizontally, however you think about it. I'm going to go with the way that Olivia kind of explained it, is that we add a column to the right. With 1 more dot. If that doesn't make sense to you, maybe you thought of it separately, you might want to explain it differently than that. Not separately, differently. I don't know what I'm saying. Math. Words. This is a very wordy unit.
It is.
Not great.
All right, so that top term we talked about, that inductive reasoning, that really means that we are using what we see or what we're given to make a guess. We have to have it, we have to see it in order to make our conjecture. Later we're going to talk about other kinds of reasoning where we kind of look at what's missing or we look at some clues and combine our ideas. But for inductive reasoning, we really want to think about what do we have, what would come next. We're looking at those patterns.
All right, we have one other part. Counterexamples are going to be really important, especially when we come to things that aren't always true. Okay, so have you ever had a parent tell you, like, I don't know. Never mind, don't say that. Have you ever had a friend tell you, like, I can jump 10 feet in the air? And you're like, prove it. Okay, you're seeing, can they jump 10 feet in the air every time? Counterexample is similar to that. We're showing why it's not always true. Why a conjecture. I can't think. I'm going to stop talking. Counterexamples show us why a conjecture isn't always true.
So you might have heard a similar idea with that word counter, like a counter offer. If you want to buy a car from someone and they say, okay, the car is for sale for $10,000, you want to offer something else. You might counter that. So you might say, no, I'm going to give you 6.
And then they might go, 6 is too low. How about 9,500?
And then you could offer, no, I can do 7.
And you go back and forth.
Go back and forth. That countering, that kind of back and forth is like showing a different option or giving another option. So we're going to use counterexamples as a way to show why our conjecture might not be true. All
right, so here our first conjecture says, after school, I ride the bike. So the thing with a counterexample is it still has to be applying to the same situation. So our situation here is after school. So we're going to say after school. I don't think there's supposed to be a comma there, is there? After school, what's something that you would go against riding the bus home? What's something that you do that's not always riding the bus home?
Walk. Drive.
What? Drive. Maybe you get picked up. I get picked up from who? Who picks you up after school?
Mom, dad, brother, sister, grandma,
Yeah.
grandma, or nearby.
I get picked up by my best friend.
Sure.
What is your guys' new initial? BTF? Best friend?
BSF.
BSF. BFF? I would do BFF, but for some reason it's not changing to...
I'm doing BSF.
Okay. Which just stands for best friend, right?
Friend.
So weird to me.
With the S.
And best.
Best.
Whatever.
Friend.
Alright, what's another thing I heard somebody say? After school, what else could you be doing? You could be...
Okay, after school I have art club.
If you go to art club, do you get on the bus right away after school? Nope. So the thing is, it has to apply to the same situation. So on this next one, it says conjecture. If, what is this? Think back to chapter 1.
Yeah, this is kind of what we worked on in chapter 1. How would we name that?
Yep, what does that symbol in the middle mean? They're equal, they're the same. What's the geometric word we use? Congruent. Okay, they're congruent, but what is this first part? Is it a line, a segment, an angle, a ray? Segment. So segment AB is congruent to segment BC. Remember, segments means they have endpoints. It's telling us that if that's the case, then B has to be a midpoint. So we need to come up, this time we're going to draw a picture of why that's not always true. So we have to think, how can we draw something where AB is the same as BC, but B isn't the midpoint? So I'm going to start by drawing AB. Janae, it's good. If you would like to be more protected, you can choose to wear a mask. Yeah. Alright, where can I draw C so that it's the same distance away from B as A, but we don't want it to extend, because if I go this way, if I put C over here, then B would be a midpoint. So where else could C be located? If I put C over here, then it wouldn't be the same distance. Does it say that they all have to be on the same line? No, what's that word for being on the same line? Collinear. Does it say A, B, and C have to be collinear? No. So what if I put C up here? Khadijah got it. She was like, is B now the midpoint of AC? No. How can I show that AB is congruent to BC? Yeah, that little tick mark. Or you could label it. You could say that this is like 3 inches and this is 3 inches. You could do it that way. Or you could do the tick marks.
What are those lines in the middle called?
We call them tick